In this lecture, we're going to talk about triple integrals. And let me start by talking about some applications of triple integrals. We saw last time that if you have a thin plate with an uneven density, maybe you have a density function delta of xy, that the double integral of that density gave you a mass. Basically because you're taking each little piece of the thin plate and multiplying the little bit of area by the density, which gives you the mass of each little piece, and then you just add all of those up. So in the same way, if you now have a three-dimensional solid with a density function delta of xyz measured in something like maybe kilograms per meter cubed, for example, well, if you split your region up into a bunch of very small pieces and multiply the volume of each piece by the density of each piece, then again you will get a mass. You might also want to find the average value of a three-dimensional function. Say you have a function f of xy. Well, then the average value of that three-variable function on the solid region D is going to be 1 divided by the volume of that region D times the triple integral of f of x, y, z dv. And you can also find things like the centroid, center of mass, and so on. All those things that we talked about for double integrals, where your region was just a thin plate, sort of a two-dimensional region, all those things work in a very natural way for three-dimensional solids. Well, I'm maybe getting a bit ahead of myself. I haven't yet defined what a triple integral even should be. But in some sense, the jump from 2 to 3 integrals is sort of not as severe as the jump from 1 to 2. At this point, we kind of have an idea that if your region D, for example, is a box, that what you would like to do is sort of split that box up into a bunch of little sub-boxes. Sort of sketch that out here. So you've sort of split it up now into a bunch of sub-boxes. And then what you can do is for each of these little pieces, you want to do something like take f of some sample point in that piece times the volume of that piece, which we call delta v. And in this case, delta v is going to be delta x times delta y times delta z, just the product of the three dimensions of each little box. And so what you would want to do is something like add up all of those. And since you're adding these up in three dimensions, you end up with a triple Riemann sum of all this stuff. But then really what you want is the limit of that as the number of pieces in every dimension goes to infinity. And that's what a triple integral is going to actually represent. Well, just like with double integrals, we're never going to calculate a triple integral using this limit definition. Instead, we want to try to find kind of an easier way. So for us, that easier way is going to be to do, again, sort of an iterated integral. And so let's start with the example of a triple integral over a box. So if you have a box, then you might have some dimensions, say from, maybe let's call the x dimensions x0 and x1, and then y0 to y1, and then z0 to z1, right? So in practice, these will be actual numbers. It could be something like from 2 to 4 in the x direction, from 1 to 5 in the y direction, and from 0 to 3 in the z direction, say. And so then for a box, just like how a rectangle was the easiest region to do a double integral over, well, in this case, a triple integral is simple to set up. So the triple integral of f of x, y, z over a box that looks like this will be something like the integral from x naught to x1 of the integral from y naught to y1 of the integral from z naught to z1 of your function f of x, y, z, dz, dy, dx. And again, you just sort of work on this from the inside out. So when you're doing that very inside integral, you're treating z as a variable, and x and y are both constant. And then when you do that integral, you'll get an answer which may very well be a function of x and y. And then you'll take that function and kind of do the double integral that you get. Well, let's do a concrete example here. So let's find the triple integral of the function 1 plus sine of x plus y plus z over the box where the range of x values is 0 to 3 pi, the range of y values is 0 to 2 pi, and the range of z values is just 0 to pi. Well, so we just set up the integral. We could say put the x bounds on the outside here, 0 to 3 pi, then the y bounds, then the z bounds. The function here was 1 plus sine x plus y plus z. And then we just make sure that we match the bounds up with the right variables. The inside bounds from 0 to pi go with dz, and then the middle ones go with dy, and the outer ones go with dx. Okay, so let's do that inside integral. So I want the integral of 1 plus sine of x plus y plus z dz. The integral of 1 is just z, and the integral of sine of all of this stuff is minus cosine of all of this stuff. In principle, I should maybe do a substitution to integrate sine, but it turns out that the substitution is pretty simple in this case. You can just take the derivative of this function here and see that you do in fact get 1 plus sine of all of that. So that's from z equals 0 to z equals pi. So plugging in pi gets you pi minus cosine of x plus y plus pi, and then minus 0 minus cosine of x plus y, well, plus 0. So pi minus cosine of x plus y plus pi, all of that plus cosine of x plus y. So you see we did the inside integral, and that took care of all of the z's, and now you have a function just of x and y. And so now if we wanted to, we could, just sort of make some room right here. So we could now go on, and we'd have the integral from 0 to 3 pi, of the integral from 0 to 2 pi, of all of that, pi minus cosine of x plus y plus pi, plus cosine of x plus y, dy dx. And so at this point, we just have a double integral. And we're not done, but from here is kind of straightforward to do with what you already know. So maybe I'll leave it just right there. So triple integrals over boxes work really easily. The real sort of difficulties will come when you start trying to integrate over solids that are not boxes, and we'll talk about one of those next.